Okay, hello everyone, and welcome back. So today, for the week, I guess it's 2 or 3, depending on how you're counting it, of the course, we're going to be covering, in the first part, linear regression. And actually, we're going to include in linear regression, we're going to take a wide view of what linear regression means. And that means any model that can be fitted to a proportional constant. What does that mean? Well, it just means that if I can say x or y is equal to, let's say y is equal to mx plus b, is an example of a standard linear regression. I mean, obviously that's an equation of a line. However, only because you have a coefficient of m and x being an independent variable, and m is a single proportionality linear to that. We can also take the view that y equals mx plus some other term, say like x, or say another coefficient, a times the ln of x plus b. And we can define this also as a linear regression if we're just trying to find the coefficients of a, m, and b, because to each one of these, y is just a proportionality to some coefficient of x, because after all, you can treat ln of x as a whole new variable, independent variable in and of itself. An example of not a linear regression would be, in this case, y is equal to mx to the b, where b is a power that you're trying to solve for, because b in this case, in this model, would actually be not a proportionality anymore, and so no longer a linear regression. But for our purposes, we're just going to look at a series of linear of polynomials that we can lump together as a into a linear form. And the nice thing about this is Excel gives us really 3 main ways we can approach this to find linear regression. And again, I guess just to hammer home why we want to do this, what we mean by regression, and why this is important to engineers, is because oftentimes we have to take data that we collect in the lab or in the real world and then fit an equation to it. And in this case, to give this story some legs, I'm going to start with an idea of from a regression model or from a stress strain curve, say for a material process. And a lot of you are going to be in MSc 201 at the same time now, so some of you may have had this, some of you may not have in some form or another, but just stealing from the web, I'm looking at what we call a stress strain curve. In this case, if we take a material, say like any solid rod of metal, plastic, or what have you, and we start clamping it, this bar, and start pulling on it across. In this case, that's called the strain, how far we can pull on this rod or bar, and the amount of force we require, the stress that's applied to that. Now, as we pull this across, there's going to be a proportional line initially that tells you how well this material resists being strained upon. And the greater the stress that's required to deform it or to pull it, obviously the stronger the material. And we call this slope initially the modulus, or the Young's modulus of the material. So in this case, if we can just apply, and obviously a slope is just another equation for the line. So in this case, if we have a stress strain curve, in this case of raw data, where we have strain, which is a unitless term, it's the amount that's moved over the initial length of the rod or the bar, and then the stress that was applied, oftentimes in megapascals, we can plot this and we get what we call a nice, what we can see is a nice line. And this is just an example of that. Now, if we actually want to find the slope of that, you've already seen last time one way we can do this, by adding a trend line. We can add a linear trend line. We can go down. In this case, we know it's going to go through 0, so we can set the intercept to 0. And we just display the equation on the chart, display the modulus, and we have a nice trend line. That's just one way of what Excel is telling us this material is, what this modulus is. In this case, it's 1.7 or 1700 megapascals, or 1.7 or 1.8 gigapascals. But what's actually happening? What do we mean by that? Well, when we take in a regression, what it's really doing is it's trying to find the equational line that looks at where every data point is along this line and sees how far off that value is from the actual model in there. And as this as the data point becomes further and further off, the worse and worse the fit is, obviously. And so we can just find a line that minimizes that distance between where the line is, where the actual line is, and where the data point is. And in that point, we can solve for this this equation. Now, that probably is a little confusing, so let me rephrase it in a different way, actually just showing you the numbers. So let's create a column of data that's based out of our model. We're going to call it Y model here. And in this case, we're going to base it off of our slope of the line. And here we know the slope is equal to 1793.5, because that's what this was. And we know this Y model is simply Y is equal to mx plus b. So Y is equal to m, and I'm going to say m is here. Remember, hit F4 to lock that in, times x, and we have that. You can copy this down, and we'll get the data points there. And so we have that. Now, if we want to find the distance, or some distance of how far off this model is to what the actual raw data is, well, we can actually take a what we call the residual. Oh, why did I say residual? And that is nothing more than the difference between these two values. We're just subtracting one versus the other. And we can go down, copy those down, and we get this nice little system. Now, if I was to sum up those residuals, you could say that, well, that would be okay because well, this should give us a total distance away from those points. However, you'll notice some of these values are negative and some of these values are positive. So it doesn't actually give us an absolute value of the distances between them. It's giving us some sum of positive and negative values. And we want to treat every deviation, whether it's negative or the line is above the value and gives us a negative value, or whether it's below and gives us a positive value. We want to treat all of those in the same magnitude. So we can do that by actually squaring this value. And in that case, we force all values square errors. And in that case, we force all of these, oops, cancel. We force all of these to be positive. And I'm going to go copy, paste, paste. And now we can call this value, sum this, the sum of squared errors. And this sum of squared errors will always have a value that's positive, and the closer this value is to 0, the better the model fit is to this expression. So in this case here, you can tell obviously because this slope is the slope of regression of 1, it's a really, really good fit. But now, what if we were to plot, and I'm going to give you as an example here, let's say we have different slopes, okay, and we're going to have sum of squared errors on this point. So what if we started off with a slope of 1,000, say? Then our sum of squared errors is actually 475.344442. If we said a slope of 1,200, our sum of squared errors is 265.1962. Okay? And if we went to 1,400, and 116.89, 1,600, I'll go 1,800, 2,000. I think you could probably get an idea of where we're going with this. But let's go to 1,600. This goes down now to 28.26. 1,800. This goes to 0.0322. 22,000. 32.2042. And 2,200. 124.776. So I'm actually going to just I will and 22,000. That was 32.2. Okay, and so now if we actually plotted this whole thing together, insert, and here, actually, and in this case, for the sake of visualization, I'm going to redo this as a connect the dots plot here. There you go. You can see clearly that we have a minimum value at which this squared errors fits. Any value on the slope line that's down here below, this is the slope, this is the sum of squared errors, how bad the fit is for each plot. You can see that there's a minimum value at which this regression line fits the data the best. Now it may not always be at 0. That value depends upon the actual quality of or how much errors in the data and so forth. But the one that fits the data best is going to be the one where this is at a minimum. And that is the heart of all regression methods. Now, and that's, I think, the short and long of how all this is going to work. And the nice thing with this is there are lots of ways we can do this in Excel. And in particular, there's a lot of ways we can do nonlinear regression. We'll talk about that a little bit later. But for the next few videos in this series, we're going to be showing you different ways of doing the linear regression and ways of calculating this value, and in terms of also reporting on how good the fit is. You'll notice we give this value the r squared, and so we'll talk a little bit more about what this actually means and how we can use that as a reliable metric. And so from there we will just stop there, and thank you.